On to a couple of examples of forces between wires. Our first example is actually just finding the magnetic fields from a couple of wires. So for one of these wires, the current is coming out towards us, and for the other it's going in. So that means that the magnetic fields are going to be swirling in opposite directions. But if you look at the region in between the two wires, the magnetic fields are actually heading in the same direction. So we want to find the magnetic field right there at a point in between the two wires. So we can use our wonderful equation for the magnetic field from a wire and plugging in our new constant, the permeability of free space. The total magnetic field is going to just be the sum of the magnetic fields from the individual wires, because that's how vectors work. And so if we have mu naught I1 over 2 pi R1 plus mu naught I2 over 2 pi R2, then we can use the fact that they are equidistant from each other, so those R's are equal, and we can factor out all the stuff that they have in common. So we're going to have mu naught over 2 pi, and we'll just call it R here, and that's going to be multiplied by I1 plus I2. We can go ahead and plug in some numbers here. You might notice this has a factor of pi in it, and we've got a factor of 2 pi in the denominator there. So we can actually cancel out essentially the 2 pi with the 4 pi and just be left with 2 here. That's not what mu naught is equal to, but that's what we're going to plug into our equation. So we're going to have 2 times 10 to the negative 7th over r, which is 5 centimeters or 0.05 meters, times the current in each of these. One is 7 amps. And the other is 5 amps. I guess I plugged those in backwards, but we're adding, so it doesn't matter. And then you go ahead and compute that, and you get a field of 4.8 times 10 to the negative 5th Teslas. And there you go. Oh, I should mention one other thing. We did kind of a nice problem where the directions of these magnetic fields were identical. If we did some point, say, over here, then we would have this guy pointing off in that direction, and this guy would be pointing off in that direction, and you would still be summing them as far as vector sums go, but you would have to take into account the different directions and do a bit of trigonometry to get the actual sum. So look forward to that. Okay, let's look at one last example here. If we say that we have one wire suspended, maybe tied off on the end somewhere, and we could create enough force, magnetic force, to lift that wire up such that it's levitated, this bottom wire here. In that case, we would have the magnetic force from the interaction between the two wires actually equal to the gravitational force. Again, we're going to use one of the equations that we just derived, this guy right here, and we're going to set that, this means magnetic force, F of B, so we're going to set the magnetic force equal to the gravitational force such that it will levitate. The magnetic force is this guy here times L, 2 pi times separation distance. We can set that equal to mg. And if we look at what we're given, we have I1, mu naught's a constant, 2 pi, obviously we're given the separation distance. We don't have L, and we don't have the mass. Well, we also know g. What we do have is the mass per unit length. So if we divide both sides by the length, then this goes away, and here we've got a term of mass per unit length where we do have that. So at this point, it's just a matter of plugging in quantities. I'm going to go ahead and cancel that out and cancel the 4 pi part of this out. It's kind of an ugly way of doing it, but anyway, we end up with 2 times 10 to the negative 7th. There are some equations that don't have a 2 pi in it to cancel out, so you will plug in 4 pi times 10 to the negative 7th on occasion. So multiply that by I1. I2 is what we're solving for. The separation distance is 20 centimeters or 0.2 meters. Now this mass per unit length is 0.12 grams. We want that in kilograms since we're dealing with newtons here, so we need to have kilograms. So 0.00012 grams per unit length. It doesn't really matter what it is. And then we're going to plug in 9.8 here, and we go ahead and solve for the current in the other wire, and we get 14.7 amps. That's all. See you next time.